Hello, welcome to this video. This is 5-1. We are talking about maximization and minimization, often referred to as optimization problems. These are going to be word problems, and they're similar to related rates. I think they're easier than related rates. We don't have to worry about implicit differentiation, but they are going to involve word problems. I'm going to split this into two videos. We'll look at one problem in each video. And first, let's go ahead before example one. Let's look at the procedure. So here we have the procedures, steps 1 through 5, and I'm going to model these when we dive into example 1. Okay, so I'll read example 1, and it says a box with no lid is to be made up from 48 centimeters squared of material. If the box must have a square base, find the dimensions that produce a maximum volume. So I want to maximize the volume. I want this box to be as big as possible, okay, with regards to volume, space inside. So step 1, it says choose variables and or draw a labeled figure. We have a figure, and I want to go ahead and label this. I know that this box has a square base, so I'm just going to use S and S to represent a side. I know those are the same. And then I have the height. Step number 2, it says write a primary equation. Okay, well, I know that volume of a box is length times width times height. So that is S squared times height. Okay, and then it says isolate to be whatever is maximized or minimized. Well, I already have volume isolated. Woo! I already have volume isolated. It's by itself, okay? So then number 3 says rewrite with only one variable on each side. This may require a secondary equation. Secondary equation. Okay, well, let's go ahead. Let's go back to the box and the other piece of information they give us. They tell us that the box, which has no lid, is made from 48 centimeters squared. Okay. So that will come into play, but what I want to do is I want to think of what's another type of formula that involves objects, and that is area, right? If I want to talk about the area of this box, okay, so area is going to be equal to, and you got to think about this, it has no lid. So I have this side here, okay, which we know is H by S, and then I have another one, and another one back over here, and then another one over here. I have 4 of those, okay, so that's 4SH, and then I have a base, which is S squared. Okay, so that is area. Now, what I want to do is I want to go ahead and isolate a certain variable, and we're going to replace it, okay? And so what I'm going to do is I'm going to isolate H. So let me manipulate this problem. I want to have area. I only want one variable, so what's the area? Well, how much is this box made up from? And that is 48 centimeters squared. So I'm going to take the information that's given, 48, okay, and I'm going to replace that with A, and now I'm going to isolate H. So 48 minus S squared is equal to 4SH, which tells us that H is equal to 48 minus S squared over 4S. Okay, so now I know what H is. Okay, well, I can just go ahead and directly substitute. I have volume is equal to S squared times 48 minus S squared over 4S. Okay, and then what I can do after I reduce, so I'll reduce this, reduce the S. This gives us S times 48 minus S squared, okay, over 4. And what I'll do is I will distribute. So 48 divided by 4 is 12. So this gives us 12S minus S 1/4 S cubed. Okay, so there is your volume formula after you simplify that problem. Okay, so that was step 3. So note that I have nothing but one variable on one side. Okay, and then now what I want to do is step 4. I need to find the domain. I need to find the domain of this box. What's possible? Okay, and we're talking with respect to our variable, which is S. So I'll write over here step 4, domain. So I'm going to ask you guys a question. What is the smallest that S could be? Well, it could be 0, maybe. Not really, then you wouldn't really have a box, right? Okay, but what's the biggest? Well, if we think about what if this box has no height? Like, what if I just get rid of the height? Then it's just all area. Well, that area is 48 centimeters squared, right? So that would be S squared is equal to 48. Okay, that's with no height. So then I can take the square root, and this is the max of the side length. Okay, square root of 48. That's with no height. So can't really be that. You would have no box. Okay, so I'll just set the lower and the upper bound, and there it is. All right. Step number 5, it says take the derivative, find the critical numbers, and make a number line. So here is where this comes into play. Okay, so I'm going to go ahead. Step number 5, I'm going to take the derivative. Okay, so we get 12 minus, I'll use the power rule to give us 3/4, and this would be S squared. Okay, so this is V prime. Okay, so I want to tie this back to the last unit. How do you find where max and mins are? Well, you find the critical numbers. Okay, so I have V prime found, and what I'm going to do is I'm just going to set this equal to 0. So 12 minus 3/4 S squared equals 0, and now we'll solve. So negative 3/4 S squared is equal to negative 12. We'll go ahead and multiply by the reciprocal, so negative 4/3. Negative 4/3. We get S squared is equal to 16, and thus S is equal to plus or minus 4. Well, negative 4 is outside of our domain, so we just kind of throw that away. And then we're going to go ahead and create a number line. So I know 0 is my minimum. I know square root of 48 is my maximum. And I know I have a critical number at 4. So I want to go ahead. I want to test some numbers. Why not test 1? And then why not test 5? I think 5 is a good number. Okay, so we'll go ahead and plug these in. Okay, so if I plug in 1, I get 12 minus 3/4, so this is definitely positive. Okay, I know my function is increasing up until 4, and then I'm going to go ahead and I'm going to plug in 5. Okay, so if I plug in 5, we get 3/4 of 25. I'm just going to make this over here. So 12 minus 3/4 of 25. Okay, and this would be 48/4 minus 75/4. So this is negative. Okay, so I know my function is decreasing. All right, so I mean, what does that make for it? It makes them a maximum point. Okay, so what this tells us is it tells us that the volume is maximized when S is equal to 4. Okay, so I want S to be equal to 4. And now that I know what S is, I can go ahead, I can find what H is by plugging in 4. Okay, so I know that H is equal to 48 minus S squared, that's 16, all over 4 times S, which is 4, so that's 16. Okay, and we get 32 over 16, which is 2. All right, so what is our conclusion? So we'll go ahead and make a conclusion. Running out of space. It's all right, conclusion. Okay. We can say the dimensions that produce a maximum volume are a side length or you could say width, I guess, side length of 4 centimeters and a height, it's a small box, of 2 centimeters. All right, and there is our conclusion. I wanted to recap. I'm going to go back over this. So again, we wanted to find the maximum volume, so we labeled a picture. We came up with an equation involving the dimensions given, and what we really wanted to do is make it in one equation. So I had to find a secondary equation, okay? And what we did was we plugged in information given to find to isolate one of the variables, and then we replaced it. When we did this, we came up with a equation for volume that just involved one variable. We took the derivative and we set it equal to 0 to find a critical, to find a max or a min. In order to know if this number s was a max or a min, we had to go ahead and test. We had to see, okay, is our function increasing or decreasing or increasing to create a max or a min at 4. We found out it was a maximum, which is what we wanted. We wanted to maximize the volume, and then we plugged it back into the equation for height to find out height, and we came to this conclusion. All right, that's it for this video. I'll go ahead and make another video for the second example. Peace. Catch you next time.